Hello, my name is Ethan Canzini and welcome to my dissertation presentation titled Metrology Assisted Assembly Process to Improve Landing Gear Installation Accuracy. This presentation will cover the current state of the landing gear installation, along with the aims and objectives of the project. Then, the current metrology processes, along with the innovative IoT methods will be introduced and placed in context of smart aerospace manufacturing. After this, the research methods for the project will be reviewed and how they will be used in the experimentation. This research will cover the sensor research and the feedback loop implementation for manufacturing. The research section leads into the details of the experimentation and provides a video demonstration of the three scenarios used to test the hypothesis. The final slides will cover the results of the experimentation for both the sensor estimation algorithm and the sensor fusion network in the manufacturing process. This is then coupled with the conclusions drawn from the project, along with the recommended further work. The wing-based landing gear is the final part of the assembly process of the AIRBUS manufacturing line plant in Toulouse. The landing gear component can weigh up to 5,000 kilograms as inserted into the rib frame of the wing structure. This substructure is governed by tight constraints and low tolerances for components due to the enclosed nature within the wing frame. The landing gear trunnion shown in Figure 2 must be precisely aligned with the axle pin to ensure smooth operation during flight. Currently, the assembly process involves inserting the landing gear trunnion, measuring the tolerances along the axle hole, and reinserting the trunnion until the tolerances are within the specified region. This process can require several attempts and a long duration to complete, thus increasing the time to completion of the aircraft. In line with Airbus's drive towards smart manufacturing and Industry 4.0, this has led to the development and requirement of new assembly methods for this process. The project aims are to develop a metrology-assisted platform for the landing gear installation process that reduces the time to completion for the insertion process and improves the reliability and repeatability during the assembly procedure. The objectives required to complete these aims are to review the research literature and the commercially available sensor types, then create a model prototype of the landing gear and embed it within a closed-loop assembly process that utilizes the estimation algorithm and sensor network to correctly position the landing gear within the assembly process. Finally, a camera-based measurement system will be implemented to test the efficacy of the sensing template. Within the current state of metrology, two sets of measurement methods exist. The first are non-contact methods, which utilize electromagnetic waves and photogrammetry for component analysis, with the second being robotic arms and laser trackers for contact methods. Both measurement types are primarily used as diagnostic and offline measurement tools, with little application within the physical assembly process. Semi-autonomous methods have sought to rectify this, with cobots utilizing feedback networks into manufacturing. However, they have limited effectiveness due to their size and the propagation of errors through their joints. In recent years, large volume assembly processes, such as the marrying of aerostructure components shown in Figure 5, yield more accurate results when compared against the traditional methods of aircraft assembly, but still retain errors in the final process due to the sensor noise and no pose validation across each axis. Due to the increasing tolerance requirements in aerospace manufacturing, sensing techniques have evolved to include hybrid methods that utilize various technologies in unison with each other. Figure 6 shows how, over time, the accuracy of these systems decreases for the benefit of the assembly process and allowing for more accurate pose and positioning. These hybrid systems have led to the development of large-scale assembly methods that have a feedback loop for positioning of components and implement 3D modeling for accurate component placement. What's more, hard real-time systems have led to the requirement that they contain online error compensation for metrology-based systems to ensure the correct pose of the component is achieved during assembly without needing post-operation assessment on the production line. In the sensor research, it was discovered that individual sensors each have their own benefits and trade-offs, as shown in the comparison table. When used independently, these sensors would be inappropriate for precise component positioning. However, complementary sensor fusion combines the sensors into a network that reduces the overall error in the system, thus improving its accuracy. For our implementation, the two sensors for each axis are a limit switch, which provides close-range accurate placement, and a microphotonic IR sensor for pose estimation over a longer range. Most aerospace assembly procedures are performed by operators rather than by autonomous machines. This means the alignment is performed with assistance provided by the sensor network. Feedback of the pose of the component is provided by the sensors in a manner that informs the operator of what movements to make next with the component. Figure 10 illustrates the feedback loop, where the sensor and encoder measurement values dictate the desired set orientation and pose of the component during assembly, along with the desired movement of the machine for the accurate alignment. For the proposed solution implementation, the sensor network provides two levels of pose detection. The first being within the close range proximity using the limit switch for sub 10 mm domain accuracy, and for longer distances using the IR sensor combined with a Kalman estimation algorithm to accurately predict the component's pose. The experiment setup is designed to replicate the aerospace manufacturing process, whilst integrating the sensor network and showcasing its effectiveness. The experiments seek to introduce the sensing template that embeds the sensors in a way that provides information about the pose of the component to the operator, and informs them when the component is in the correct alignment. These two figures show the composite model of the landing gear and the wing frame, along with the electronics and sensors embedded into the template. For the software control, the sensors are subject to a Kalman filter that provides position estimation within the sensor fusion network. The software flowchart shows how each axis is constrained individually, with each sensor providing information to the operator that dictates the movement of the component relative to the sensing template. Once both axes are aligned, the camera takes a picture of the axle hole to compute the final error offset of the assembly. There are three scenarios for the experimentation testing. The first scenario is the default method, where the operator must visually confirm the placement of the component after each insertion and reinsert the trunnion if the pose is incorrect. There are no sensors present for feedback information about the pose of the component in this scenario. The second scenario introduces a single sensor onto each axis, which provides feedback about the pose of the landing gear trunnion and allows the operator to use the sensor readings, shown on the left, to accurately position the component within the wing frame. The sensor is using the Kalman estimation filter to provide an accurate reading from the sensor for the operator. The third and final scenario uses both the limit switch and IR sensor on each axis that work in tandem to provide a complete view of the pose of the component and inform the operator when the trunnion is in the correct position. The limit switch will go high when the component is in the correct position, and the operator needs to move it away just enough so it goes low again. The first set of results to be analyzed are the estimation filter's performance compared to the measurement reading directly from the sensor. As shown in the graph, the Kalman estimator is capable of accurate tracking of measurement values for the entirety of the sensor's range. Additionally, its performance is an improvement over the use of the raw sensor output, shown in green, indicating that the tracking capabilities of the Kalman filter allow for greater information regarding the pose of the component. An additional benefit of the Kalman filter is the reduction of the uncertainty in the measurement value, shown in the shaded areas of the graph. The grey area is considerably less than the light blue area, indicating the Kalman filter reduces the standard deviation of the output and improves the accuracy of the reading to the operator. What's more, the R-squared metric of the estimator, where k is equal to 0.242, is greater than the metric for the raw sensor output. This shows that the estimator has a better fit to the actual distance between the component and the sensing template, further improving the reliability of the algorithm as opposed to the unfiltered sensor output. To analyze the sensor network, we must examine how the sensor fusion affects the spread of data and its distribution. Overall, the addition of the sensor network reduces the spread of the data as shown in the box plot diagram. This spread is observed in both the X and Y directions of the sensing template, indicating that the inclusion of the template reduces the offset of the component and tends the median value towards 0 as shown in the final scenario. Extracting the probability density function for each of the scenarios, we observe that across all the runs, the distribution for scenario 1 is short and narrow, indicating a large standard deviation and range of possible outcomes for the assembly process with no sensing template. When using the single sensor on each axis, as in scenario 2, the distribution increases in height and reduces in width, showing the improvement in the accuracy that the sensing template provides. The final distribution for scenario 3 is tall and narrow, emphasizing that the sensing template reduces the standard deviation in the installation procedure. What's more, with the installation of the sensing template, the mean value across each axis tends to 0, showcasing the effectiveness of the sensing template in reducing final error offset in the measurement. To fulfill the final objective, the camera implementation can be used to analyze the final offset of the assembly by using the hue circle transform. The image algorithm can determine the axle alignment as shown in the progression images here, and can find the error in the components posed to inform the operator whether the component needs further movement within the assembly. In conclusion, the proposed solution outlined in this presentation highlights how the Kalman estimator provides accurate and repeatable tracking for moving components by filtering the measured sensor values. Additionally, the introduction of the sensor network improved the accuracy of the trunnion insertion process and increased its repeatability by giving the operator more information to use during the installation. Further work to be completed in this field would be to use graph networks and algorithms to increase the reliability of sensor readings. Furthermore, the sensing template could be implemented alongside an autonomous movement method, such as a multidimensional platform, to allow for the precise control of components during assembly. The proposed solution would also benefit with being tested in a real-world production cycle to test how well the algorithm responds to the industrial constraints and limitations of a real-world manufacturing factory. Thank you for listening.